If you were forced to migrate your entire infrastructure to a different cloud provider tomorrow, um, would your current architectural design actually survive the transition?
Oh, man. That's the ultimate stress test, right? Those systems would probably just collapse under the weight of their own dependencies.
You really would. Welcome to the deep dive, everyone. Today we're doing a comprehensive analysis of the core technical material in the book, Software Architecture with C# 14 and .NET 10 5th edition by Gabriel Baptista and Francesco Buzzese.
Yeah, and our mission today is really to give you, the listener, a logical breakdown of how to build modern enterprise applications.
Exactly. We're going from basic architectural decisions through safe coding in C Sharp all the way to deploying highly scalable microservices in the cloud. So let's jump in. Building a resilient system, it really starts with the constraints, right?
Right, absolutely. Software architecture basically dictates how your system handles data or, deals with failures and scales. It's all about making those critical decisions early on. If you wait until production to find out your system can't handle the load, you're in trouble.
Because it's like a building. You wouldn't pour the foundation without knowing how tall the skyscraper is going to be.
Exactly. So when you're gathering requirements, understanding the exact load expectations dictates your whole strategy. Like if you know a system has to return search results in under, say, 200 milliseconds.
Which is pretty standard these days.
Right. But hitting that means you have to implement asynchronous programming and back-end caching from day one. You can't just bolt that on later.
Okay, but let me play devil's advocate for a second. We live in an era of massive cloud computing, right? Adding RAM or processors is literally just a configuration toggle. So do minor code inefficiencies like, I don't know, concatenating strings in C Sharp, do those still actually matter?
Oh, they pose a severe architectural threat, especially in the cloud.
Wait, really? Just from string concatenation?
Yeah, because in C#, strings are immutable. Once you create a string in memory, it cannot be changed, period.
Okay, so if a developer uses the standard plus operator to add text inside a big loop,
The application doesn't just append the text. It allocates a completely new string in memory for every single iteration, and it just abandons the old one.
oh wow. So if you have a high traffic service getting thousands of requests a second, you're just generating mountains of digital trash.
Exactly. The memory fills up instantly.
Huh.
And that triggers the .NET garbage collector to run constantly.
Right, and for those who might not know, the garbage collector is basically the automated system that frees up unused memory. But why is it running constantly such a big deal?
Because when the garbage collector does a deep clean, it actually suspends the execution threads of your application. It has to freeze things to safely move objects around in memory.
So your application literally stops working for a split second.
Yes. And if your bad code is creating too many discarded objects, these suspensions happen all the time and they last longer. Your server's processors spend more time cleaning up memory than actually serving your users.
Meaning the CPU hits 100% and the whole thing just crashes.
Exactly. So efficiency is mandatory. You have to design for vertical scaling, getting the most out of a single server, and horizontal scaling, which is distributing load across multiple servers.
Okay, that makes sense. So since minor code issues can take down the whole system, safe coding practices are crucial. And that brings us to managing unmanaged resources, like database connections.
Yeah, that's a huge one. The garbage collector handles memory, but it doesn't automatically release external operating system resources.
Right, so you have to use the iDisposable interface,
Right.
right? Or the modern using statement in C Sharp.
Exactly. If you open a connection to a SQL database and forget to close it properly, that connection just stays open on the server. Under heavy load, you'll hit your maximum allowed connections in minutes.
And then nobody else can log in. The system just halts. So implementing iDisposable basically tells the system, hey, I'm done with this resource, give it back to the OS immediately.
Right, it guarantees system stability.
Now, the authors talk about using Roslyn-based static code analyzers to enforce these rules. I kind of think of Roslyn like an automated building inspector checking your code while you type.
That's a great analogy. It analyzes the abstract syntax tree of your code in real time.
Yeah.
It doesn't even wait for you to compile or run tests. It just highlights missing disposal routines right there in your editor.
And today we're seeing AI tools like GitHub Copilot jumping into, acting like an automated pair programmer.
Yeah, they evaluate your C# code against architectural standards and suggest improvements instantly. It really helps enforce patterns like iDisposable, which makes the code way more maintainable and reusable.
Speaking of reusability, how does modern .NET actually let developers write a component once and then, run it on a Linux server and an Apple iPhone? Like, mechanically, how does that work?
It's pretty brilliant, actually. It relies on a unified runtime and something called intermediate language. When you compile C# and .NET 10, it doesn't translate it into Windows machine code.
It translates to this intermediate language instead.
Right. And then the target device, whether it's Linux or iOS, runs a specific .NET runtime. That runtime translates the intermediate language into the exact native instructions for that specific processor right before execution.
Oh, so the developer just writes the core business logic once, and the runtime handles the translation for whatever device it lands on.
Exactly. It's truly cross-platform.
That's awesome. So, okay, once we have these reusable components, we need blueprints to organize them. Let's talk about design patterns, starting with the solid principles.
Yeah, solid is fundamental for object-oriented code.
Right. So single responsibility means a class should only do one specific thing. But what about the open-closed principle? That one says a component should be open for extension but closed for modification.
Yeah, this one is critical. The mechanism here relies on interfaces and abstract classes.
Give me an example.
Okay, let's say you have a class that calculates shipping costs. Later, the business says, we need to add a new shipping provider. You should not go in and alter the existing, fully tested calculation code.
Because touching tested code is a great way to introduce new bugs.
Precisely. Instead, your original class should just rely on an interface. Then, you create a brand new class for the new shipping provider that implements that interface.
So the existing system just uses the new provider without changing any of its own internal logic.
Exactly. It makes the software incredibly stable.
Now, beyond object-oriented stuff, we have cloud computing design patterns. The book goes deep into CQRS, command query responsibility segregation. Mechanically, why do we need to physically separate the database operations that read data from the ones that write data?
It solves a massive database locking problem. In a traditional setup, when a user updates a record, the database engine puts a temporary lock on that row so the data doesn't get corrupted.
Makes sense. But what if thousands of users are trying to search that same table at the exact same time?
Well, their read operations are totally blocked until that write operation finishes. It causes huge delays. So CQRS solves this by sending all data modifications to a highly optimized write database.
Ah, and then it syncs that data over to a separate read database.
Yes, asynchronously. So search queries hit the read database, they never encounter any locks, and the application can serve massive traffic without breaking a sweat.
That is so smart. But implementing CQRS means you need really strict organizational boundaries, which leads us to domain-driven design, or DDD.
Right. DDD divides your enterprise system into bounded contexts. Like you have a context for billing, another for inventory, and so on.
And to structure these contexts, the authors recommend the onion architecture. How does the onion architecture handle dependencies compared to a classic layered approach?
Well, in a classic layered architecture, dependencies flow straight down. The user interface depends on the business logic, and the business logic depends on the database.
So if I switch from SQL Server to a NoSQL database,
You basically have to rewrite your entire business logic layer because it's hard-coded to depend on SQL. The onion architecture fixes this by putting the domain model, your pure business rules, at the absolute center.
and the rule is that all dependencies have to point inward toward the center.
Exactly.
But wait, how can the central business logic save data to a database if it's not allowed to explicitly reference the database code?
Through dependency injection. The central domain layer just defines an interface. It's basically a contract saying, hey, a method to save data must exist. It doesn't care how the data gets saved.
So the outer layer where the actual SQL code lives implements that interface.
Right. And when the app starts up, the dependency injection container links the concrete database class to that central interface. So the business logic just calls the interface, and the infrastructure does the actual work.
That's brilliant. The core domain stays completely isolated and pure. It literally has no idea what database technology is being used.
Exactly. It makes testing and future migrations so much easier.
Okay, so with the domain isolated, let's talk about how we actually build and deploy this thing. DevSecOps integrates security and automation into every phase. We've got continuous integration, which triggers automated tests whenever code is merged, right?
Right. And then continuous delivery automates deploying that code into staging or production. Plus continuous security, which is constantly scanning for vulnerabilities in the pipeline.
But managing all this requires a branching strategy in your source control, like GitHub. The text mentions GitHub Flow, which is for rapid iteration. You create a branch, do the work, merge it to main, and bam, it deploys to production.
Yeah, it's incredibly fast.
But deploying directly to production multiple times a day, that sounds kind of terrifying for a complex enterprise app. Is GitHub Flow always the right choice?
Not always, no. It requires very high operational maturity. To deploy safely like that, you need exhaustive automated test coverage, and you have to use feature flags.
Feature flags, like a toggle switch for code.
Basically, yeah.
Yeah.
It lets developers deploy new code to production, but it stays hidden from the users until the business flips the switch to activate it.
Okay, but what if a company doesn't have those safety nets, or they're in a heavily regulated industry?
Then GitHub Flow is a bad idea. They should use release flow instead. That involves creating isolated stabilization branches where manual testing and compliance audits happen over weeks before anything goes live.
Got it. Either way, deployment reliability relies heavily on testing. The book pushes test-driven development, or TDD,
Yes, you write the automated test for a function before you even write the function itself.
which forces you to design clear, testable interfaces right from the start. Once the code passes, it's ready for the cloud. Now, speaking of the cloud, let's categorize some models. What's the real difference between infrastructure as a service, platform as a service, and serverless?
Well, infrastructure as a service, IS, is like renting an empty server rack. Microsoft gives you the hardware, but you have to install and patch the operating system, the runtime, everything. Total control, but massive maintenance.
And platform as a service, PaaS.
PaaS removes the OS headache. The provider just gives you a running web server environment. You just upload your code.
Much easier. And then serverless, like Azure Functions.
Serverless completely abstracts the web server. Your app is just divided into individual functions, and the cloud provider only spins up computing power when a specific event triggers one of those functions.
And the billing model for serverless is wild, right? You don't pay a monthly fee for a server. You pay exclusively for the compute time down to the millisecond.
Exactly. If your function takes 200 milliseconds to process a photo, you only pay for that fraction of a second. But it does introduce the cold start problem.
Right, where a function that hasn't run in a while takes a second or two to initialize when it's suddenly called. Now, all this demand for dynamic scaling pushes us toward microservices.
Oh, definitely. In a traditional monolith, the user interface, business logic, and background processing are all just one giant deployable unit.
So if everyone is running complex reports at the end of the month, you have to copy the entire massive application across 10 servers just to handle the load on that one reporting module.
Which is incredibly expensive. Microservices break that monolith down into small, independent services based on those bounded contexts we talked about earlier.
Yeah.
So you just scale the reporting service independently.
Saving a ton of money. Now, the book separates front-end microservices from worker microservices. Worker microservices are like an invisible assembly line, right?
Yeah, they handle the heavy, long-running tasks in the background, generating invoices, processing payments, things you don't want the user waiting on a loading screen for.
But if these services are completely independent, they have to communicate over a network. You can't just use standard method calls anymore. How does the publisher-subscriber pattern handle this with something like RabbitMQ?
Well, in a distributed system, network failures are basically guaranteed. If service A sends data directly to service B using a standard HTTP request, and service B happens to be rebooting.
The transaction fails and the data is just gone.
Right, so PubSub uses a message broker as a middleman. Service A publishes the transaction data as a message to a queue on the broker, and then Service A just goes back to work.
It doesn't even wait for a response.
Nope. Service B is the subscriber. It constantly watches that queue. When Service B is ready, it grabs the message and processes it. And if Service B crashes, that message just sits safely in the queue until Service B comes back online.
That is incredible fault tolerance. But having all these services talking over external networks creates a huge security risk. How do we verify identity without crushing the database with login queries every millisecond?
That's where JSON Web Tokens, or JWTs, come in. When you log in, the system gives you a token with 3 parts: a header, a payload, and a signature.
And the payload has your claims like I am an admin or whatever, but that part isn't encrypted, is it?
No, it's just encoded. Anyone can read it. The magic is in the signature. The authentication server creates that signature by mathematically hashing the header and payload using a private key that only the server knows.
Ah, so when a microservice gets the token, it recalculates the signature using a public key.
Exactly. If a hacker tampers with the payload to make themselves an admin, the signatures won't match anymore. The microservice will instantly reject the request without ever having to check the database.
Wow, that's incredibly efficient. But wait, authentication is just identity. What about the actual data traveling between these services?
For that, you need mutual TLS. Both the client and the server verify each other's cryptographic certificates before they talk. And, crucially, you have to encrypt sensitive fields directly inside the database itself.
So even if a hacker bypasses the network and steals the raw database files, it's just gibberish to them without the application keys.
Exactly right. And the authors actually tie all these concepts together in a massive case study at the end of the book, the WW Travel Club.
Yeah, they use .NET Aspire for that, right?
They do. .NET Aspire handles all the insane configuration needed to wire up front-end services, worker microservices, message brokers, and databases. It ensures the whole complex architecture runs reliably, whether it's on a developer's laptop or up in Azure.
It really synthesizes everything beautifully. Well, we've covered a massive amount of ground today, from memory exhaustion in C# to onion architecture, automated deployments, and message queues. We strongly recommend that you read the actual book, Software Architecture with C#14 and .NET 10, to get the full technical depth and see the actual code samples.
Yeah, there's no substitute for getting your hands dirty with the code.
Absolutely. Friends of the show, please be sure to subscribe so you don't miss our future deep dives. Have a great day. But as you look at your own code today, I want you to consider this. If your primary database server experiences a catastrophic failure right this second, does your architecture possess the asynchronous fault tolerance to queue those user transactions safely? Or are your customers just going to get a fatal system error?